In the waterfall model, the work moves like a river that goes down one step after another. You finish one step completely before you start the next. Think of building a house. First you draw the blueprint, then you lay the foundation, then you raise the walls, then you add the roof, and finally you paint. Each of these stages has a milestone, a clear sign that says, "We are done with this part and can move on." The rule is strict. You cannot start painting before the walls are finished, just as you cannot write code before the design is approved. If any work is left unfinished, the whole project can get stuck, because later stages depend on the earlier ones being correct. Mathematically, the sequence can be expressed as a list of phases P1, P2, up to Pn, where the start time of phase P sub I plus 1 is the finish time of P sub I. Start of P sub I plus 1 equals finish of P sub I. This simple rule enforces the linear order and makes schedule calculations easy. Explanation: before any building begins, the owner writes down exactly what they want, how many rooms, where the kitchen will be, etc. In software, this is the requirement specification. It is a formal document that lists every feature the system must have, written in clear, unambiguous language. A traceability matrix is like a giant checklist that ties each requirement to the later work that satisfies it. Imagine a table with two columns: on the left you have the requirement ID R1, R2, and so on, and on the right you list the design element, code module, and test case that address that requirement. If you change a requirement, you can instantly see which parts of the project need to be updated. Example matrix: requirement design doc code module test case. R1-login D1 C1 T1. R2-report D3 C5 T4. This traceability ensures nothing is forgotten and makes audits straightforward. Formally, if R equals open brace R_1, R_2 ... R_m close brace is the set of requirements, and it equals open brace A_1, A_2 ... A_k close brace the set of artifacts, design, code, tests. The matrix M is a binary relation where M of R sub I, a sub j equals open brace 1 if a sub j satisfies R sub I, 0 otherwise close brace. The matrix helps to verify full coverage. When the design team draws the flow of a program, they can measure how tangled the logic is with cyclomatic complexity. Think of a maze: the more branching paths there are, the harder it is to find your way out. Cyclomatic complexity counts the number of independent paths through the code. The formula is V of G equals E minus N plus 2, where E is the number of edges in the flow graph, and N is the number of nodes decision points. A simple straight line program has V of G equals 1. Every if, while, or case statement adds to the count. Real-world analogy: imagine a recipe. A recipe with only one step, boil water, has complexity 1. A recipe that says if the sauce is too thick add water, otherwise add cream, then stir for 5 minutes, adds branches, increasing complexity. High complexity warns developers that the design may be hard to test and maintain, so they try to simplify it. Typical industry thresholds 1 to 10 is low, easy 11 to 20, moderate greater than 20, high needs refactoring. Productivity in coding can be measured in two common ways. Function points, abbreviated FP, look at what the software does, not how many lines it uses. A function point counts a user-visible feature like an input screen, a report, or a data query. Each feature gets a weight: simple, average, complex. The total FP equals sigma of count times weight. For example, a simple input screen equals 3 points, a complex report equals 6 points. If a system has 10 simple inputs, 5 average queries, and 2 complex reports, the FP equals 10 times 3 plus 5 times 4 plus 2 times 6 equals 30 plus 20 plus 12 equals 62. Lines of code per person day, abbreviated LOC per PD, is a more old-fashioned metric. You count how many source code lines a developer writes in a day. Suppose a team writes 12,000 lines in 30-person days. Then, productivity equals 12,000 LOC divided by 30-person days equals 400 LOC per person day. Both metrics help managers estimate effort, compare teams, and detect when a project is falling behind. The function point method is preferred because it is less affected by programming language verbosity. Analogy, think of building a LEGO house. Counting bricks LOC tells you how many pieces were used, but counting rooms and doors function points tells you what the house actually does for its occupants. Explanation. Verification, checking we built the software right, and validation, checking we built the right software, rely on test coverage numbers. A simple coverage formula is coverage percent equals number of items tested divided by total number of items times 100%. Items can be statements, branches, conditions, or requirements. Example, statement coverage. If a program has 200 executable statements and our test suite runs 150 of them, coverage equals 150 divided by 200 times 100 equals 75%. Branch coverage counts each possible true or false outcome of a decision. For an if there are 2 branches. If there are 30 ifs, 60 branches, and our tests hit 45 branches, coverage equals 45 divided by 60 times 100 equals 75%. Real-world analogy, imagine a garden with 100 flowers. If you check 80 of them for wilt, you have covered 80% of the garden. Higher coverage gives confidence that hidden bugs are less likely. In the waterfall model, coverage is measured after the implementation phase, before moving to the next stage, ensuring that the product meets the quality gate. Goal thresholds often used: greater than or equal to 80% statement coverage, greater than or equal to 70% branch coverage, and 100% requirement coverage. When a software product is ready to be installed for real users, the team makes a deployment plan that weighs the money spent, costs, against the benefits gained. Cost-benefit analysis, abbreviation CBA. Net benefit equals total benefits minus total costs. If the net benefit is positive, the deployment makes sense. Return on investment, abbreviation RO. ROI percent equals net benefit divided by total costs times 100%. Example, a company spends $50,000 on a new inventory system, hardware, software, training. The system is expected to save $20,000 per year in labor costs and $10,000 per year in error reduction. Expected benefits over 3 years equal $90,000. Net benefit equals $90,000 minus $50,000 equals $40,000. ROI equals $40,000 divided by 50,000 times 100% equals 80%. Thus, the investment returns 80% of its cost over 3 years. Analogy, think of buying a bike. You spend $200 cost. If you save $30 each month on bus fares, after 10 months you saved $300, giving a net benefit of $100 and ROI of 50%. The deployment plan also lists when the software will go live, who will be responsible, fallback steps, and how to measure the realized benefits. In Waterfall, this analysis is done after the verification phase and before the final release, acting as the last gate. Explanation: after a software product is released, it enters maintenance. 2 key numbers help us understand how healthy the product is. Defect density measures how many bugs are found per size of the code, usually per 1,000 lines, KLOC. Defect density equals number of defects found divided by KLOC. If 30 defects are discovered in a 150 KLOC system, defect density equals 30 divided by 150 equals 0.2 defects per KLOC. Low defect density suggests a stable product. Reliability modeling predicts how often the software will fail. A common simple model uses the failure rate lambda and the mean time between failures, MTBF. MTBF equals 1 divided by lambda. If on average the system fails once every 200 hours, lambda equals 1 divided by 200 equals 0.005 failures per hour. The probability that the system works without failure for a time t can be expressed with an exponential reliability function. R of t equals e to the minus lambda t. For t equals 100 hours and lambda equals 0.005, R of 100 equals e to the minus 0.5, approximately equals 0.607. So there is about a 60% chance it will run 100 hours without a crash. Analogy, think of a car that needs oil changes every 5,000 miles. If you drive 1,000 miles per month, the failure rate is 1 change per 5 months. Knowing this helps you schedule maintenance before a breakdown. In the waterfall model, maintenance is a separate final phase, and these metrics guide how much effort to allocate for fixing bugs and improving reliability. The waterfall schedule is built with two classic tools, the critical path method or CPM and Gantt charts. CPM finds the longest chain of dependent tasks, the critical path. Any delay on this path pushes the whole project back. Well, steps. 1. List every activity with its duration. 2. Draw arrows showing which activities must finish before others can start. 3. Compute the earliest start, abbreviated ES, and the earliest finish, abbreviated EF, for each activity by moving forward. EF equals ES plus duration. 4. Compute the latest start, LS, and the latest finish, LF, by moving backward from the project end. 5. The total float, also called slack, equals LS minus ES. Activities with zero float are on the critical path. Example: a simple project has 3 tasks. Task A, 3 days, no predecessor. Task B, 4 days after A. Task C, 2 days after A. Critical path equals A to B equals 3 plus 4 equals 7 days. Task C has float because the project finishes after B. Gantt chart is a visual bar chart showing each task on a timeline. The start date is the left end of the bar, the length shows duration, and overlapping bars reveal parallel work. Analogy: think of planning a road trip. The critical path is the longest leg of the journey. If you are late on that leg, you will miss the arrival time. The Gantt chart is like a map with colored lines showing when you will be on each road. In Waterfall, the CPM helps managers know the minimum possible project time, while the Gantt chart communicates the schedule to the whole team and stakeholders.